Hello everyone. So Chemistry Masters welcomes you again in our new video related to pericyclic reaction and specifically related to electrocyclic reactions. So here in this video, Chemistry Master brings you the ring opening and ring closing reaction of allyl system. The allyl systems could be your allyl cation, allyl anion and allyl radicals. So we will see that how does the HOMO of all these system will be affecting the ring closing and ring opening reactions. So before moving forward, please don't forget to subscribe our channel and like our videos.
So like as 4n pi electron system and 4n plus 2 pi electron system, the ring closing and ring opening electrocyclic reaction can be studied in allyl system also. So here first we will be taking the example of ring closing electrocyclic reaction in allyl system. So in our previous video we already have seen that there are three type of allyl systems: allyl cation, allyl anion and allyl radical. So here we will see that how these system will get close, or here we will see that how does the terminal orbitals will overlap with each other to give you a cyclic structure. Now we already know that in pericyclic reaction, the reaction can undergo cyclization in thermal condition as well as in photochemical condition. So here in these three examples you can see that in thermal condition and HNU condition the reaction can happen and the bond will break in such a manner like this, so that the terminal carbon will be getting a negative charge in this case, and that negative charge will be joining to this positive charge, so that a ring will be closed and the positive charge will be obtained at the central carbon. Similarly, in the next case, the bond will break on this side, while the terminal carbon will be getting a plus charge here. Already on the another terminal there is a negative charge, so that again a cyclic structure will be obtained and the negative charge will be obtained at the central carbon. While in the case of allyl radical, homolytic bond fusion will be there, so that the central carbon and the terminal carbon will be getting one radical each, and the terminal carbon will be completing the cyclic structure and the central carbon will be getting the radical. Now here we will take all these system one by one and see that how the cyclization will take place. So at first we will be taking the example of allyl carbocation. There are three molecular orbital in the case of allyl systems. Those are psi1, psi2 and psi3, where psi1 is your bonding orbital, psi2 is your non-bonding orbital and psi3 is your anti-bonding orbital, which is designated with a star. Now we will see that how in thermal condition the molecule will undergo. So for that we will take the thermal condition. So for every molecular orbital there will be fulfillment of electron that will be carrying according to a general rule of chemistry. So as there are three molecular orbital, there should be three electron, but as you can see there is a positive charge, so overall there will be two electron in the system. So those two electron will be filled here in thermal condition. So this molecular orbital where the electron has been completely filled is your HOMO, while psi2 will be LUMO. And we already have discussed in our previous videos also, whenever in electrocyclic reaction the ring closing is happening, the HOMO is the orbital which is undergoing the ring closing system. So here if you talk about the ring closing, we will be taking this system. So here what is happening, the two orbitals which are shown here, they will be resembling the molecular orbital which is highly occupied molecular orbital, that is your HOMO. So here psi1 is our HOMO. The second thing which is very much important is the symmetry. If you see in the system, we haven't shown the central orbital out here, that generally is shown like this, where only the terminal orbital are shown. So by these two terminal orbital we can decide that which type of symmetry will be there. So if you take imaginary line out here like this, if you get the same type of orbital in opposite direction lying on the same side, you will call it as having mirror symmetry. So here it is mirror symmetry present in the molecule. So now we will see that how you will get the cyclic structure. We know that same type of lobes should be interacting with each other so that the bonding orbital can be obtained. So here what will happen? The two same type of lobes should interact. That is, either positive lobes might be overlapping with each other, or maybe the negative lobes should be overlapping each other. So here we have shown that the positive lobe are overlapping with each other so that the bonding orbital occurs and there is cyclization. Now here we will see that how does this the same type of lobe will be interacting with each other. So for that we have to move the orbital in such a way so that they can interact. So here what can I do? I can rotate this orbital towards my right hand side while this orbital towards my left hand side. So you can see the opposite direction movement is there. That's why there will be this rotation and we will be getting this cyclized structure. Now, another thing which is very much important in any electrocyclic reaction is that the reactant and the product should have same symmetry. So we already have said that the reactant is having M symmetry. Let us see that whether the product is having M symmetry or not. So for that what we can do, we can imaginarily cut the structure from between, and if you see, if I go to my right hand side and if I go to my left hand side, I am encountering the same type of structure. That's why you can say that M symmetry is preserved, and whenever same symmetry is there, we can say that the product will be formed with the help of that reactant. Now let us see that what will happen in H nu conditions. So whenever we are taking the H nu condition, or you can say the photochemical condition, in that case one of the electron from the lower energy level get jumped to high energy level like this, so that this will become your HOMO and this side 3 star will become LUMO. Now we already know that the HOMO is the orbital which is undergoing a reaction, and here cyclization reaction. So in this case you can see the arrangement of the orbital is resembling the side 2 molecular orbitals, where the two terminal orbital are lying in such a way that if I cut it from between by an imaginary line, on my right hand side the arrangement of the orbital is different as compared to the orbital on my left hand side. So that you can say that this is not having mirror symmetry, and whenever there is no mirror symmetry, there is C2 symmetry. In H nu condition, side 2 will be our HOMO while the symmetry should be C2. Now here we will see that how does the cyclization will take place. So again, for cyclization it is very much important that same type of lobe should be interacting with each other. That means, as we have shown here, the positive lobes are interacting with each other. Now we will see that how this interaction will take place. So if I move it on my right hand side, then here what I have to do, I have to move this orbital also toward my right hand side so that the same type of lobe can interact with each other. So that you can say here the cone rotation is required for cyclization. Now if you talk about another very much important condition, that is the reactant and the product should have same symmetry, or you can say the symmetry of the reactant should be preserved in the product also. So for that I have to see that whether this structure, that is the cyclic structure, is having the C2 symmetry or not. For that I have to see that if I pass through the center of the molecule from one side and reaching to the equal distance on the other side, whether I am getting the same type of arrangement or not. For example, if I am moving from here, from the center of this white lobe on my left hand side, passing through the center, and in the equal distance if I am moving towards my right hand side lobe, the white lobe, I will be getting the same type of arrangement. That's why you can say that this is having C2 symmetry, and this is very much important to understand that in sigma bonding orbital M symmetry and C2 symmetry both are present. That's why we can say that in HNU condition, cone rotation will be required and C2 symmetry will be there in the molecule. Now we will take the example of allyl anion. So again, likewise our allyl cation, allyl anion also have three molecular orbital, where the lowest one is considered to be as the psi1, which is bonding orbital. The intermediate is your psi2, which is non-bonding orbital, and the highest one is your psi3 orbital, which is anti-bonding. That's why it is shown as psi3 star. Now again we will be taking the ring closing reaction in thermal condition. Now if you talk about the number of electrons, so overall you can see there are 4 electrons, 2 pi electrons are there and 2 electrons are present here. So 4 electrons are filled in such a way that your psi2 become HOMO and psi3 star become LUMO in thermal condition. Now we will see that how does the cyclization take place. So if you remember, we have said that the HOMO in any condition will be the molecular orbital which is undergoing cyclization. So here you will see that the arrangement whatever is present in psi2 is shown here, because psi2 is our HOMO and which will be undergoing cyclization. Now again the next thing which is very much important for us, we have to see that what is the symmetry present in the molecule, because symmetry will tell that what type of rotation will be required by the molecule so that it can undergo cyclization. Here again if I cut the molecule from between, and if I see on my right hand side and on my left hand side, the arrangement is of different kind. That's why we can say that there is no mirror symmetry, and wherever there is no mirror symmetry there is C2 symmetry present. Now the next thing which is very much important for cyclization, there is need of interaction of same type of lobes. So here if you see the product, two same type of lobes are interacting which are considered to be positive lobe. So how they will be coming near each other? So if you are rotating them on the same direction, that is for example I have rotated them on my right hand side, then the same type of lobe will be interacting with each other so that there will be bonding between the lobes and the cyclization will occur. So you can say that there is need of cone rotation. So again another thing which is very much important is that the symmetry of the reactant should be present in the product also. So here also we already know that whenever there is a sigma bond formation in sigma bonding orbital, the C2 symmetry and M symmetry both are present. So default there will be C2 symmetry present in the molecule. Now we will see that in HNU condition what will happen. So in HNU condition, one of the electron from the higher filled orbital, that is your psi2 here, will get excited and reach to psi3 star, so that our psi3 star will become HOMO in this case. So you will see that the HOMO, that is psi3 star, will be undergoing cyclization in this case. So here again very much important is that psi3 star is our HOMO. And if you see the symmetry, if I cut the molecule from between, on my right hand side and on my left hand side same type of arrangement is present. That's why there is mirror symmetry. And the next thing which is very much important, that is the interaction of the same type of lobe so that cyclized product can be achieved. For that I have to rotate the two orbital in such a way so that they can interact with each other. So here what is needed? We have to rotate the two orbital in such a way so that they can interact. So one of them will be rotating on my right hand side, another will get and rotate on my left hand side, so that the bonding interaction take place and the cyclized product will be obtained to us. So here you can see that two orbitals are moving on the opposite direction to each other. That's why there is disrotation. And the another thing which is important is the symmetry should be present in the product also. So here already we have said a number of times that the sigma bond which is formed, it do have both C2 symmetry, M symmetry. So default also here M symmetry will be observed in the molecule. Now the another example is of allyl radical system. So where you can see there are overall three electrons present. So 2 pi electron and 1 electron is here. So overall 3 electrons will be there. So they will be filled in these 3 molecular orbital of allyl radical. So again, psi 1 bonding orbital, psi 2 non-bonding orbital, and psi 3 anti-bonding orbitals are there. Again, we will be taking the thermal condition where these 3 electrons will be filled. So here likewise allyl anion HOMO is our psi 2 in thermal condition. So what will happen in this case? The psi 2 is HOMO where there is C2 symmetry, and for cyclization we will be requiring cone rotation and we will be getting the cyclized product. And here also what will happen, the symmetry of the product will be resembling the symmetry of the reactant. That is, here also in the product there will be C2 symmetry. Similarly, if we talk about HNU condition, this is a special case where each and every molecular orbital is having a single electron in it. You can go through our previous video. The link about that is present in our description also. So if you talk about here, the psi 3 star will be the HOMO in HNU condition, where you can see mirror symmetry is present. So psi 3 star is HOMO in HNU condition for allyl radical. Mirror symmetry is present in the molecule. So whenever there will be mirror symmetry for interaction between the same type of lobe, they would be moved in opposite direction to each other, so that you can say that there is this rotation, and when you rotate them in opposite direction, the cyclized product will be obtained to us, whose symmetry will be same as the symmetry of the reactant, so that bonding orbital can be achieved. So these are the 3 different ways in which allyl cation, allyl radical, and allyl anions get cyclized into their respective product. Here now we will be taking the example of a ring opening electrocyclic reaction in allyl system. So we already have said that we are having 3 allyl system. One is allyl cation, another one is allyl anion, and the third one is allyl radical. So previously we have seen that from these allyl system, how does the cyclic structure can be obtained. Now we will see that how these cyclic structure can be opened to give you the allyl systems. So opening of these cyclic structures is very simple. So we have to break the bond in such a way that this single bond breaks towards our left hand side, so that the left hand side will be getting a negative charge. This negative charge which you will get at this position will be joining with this plus charge to give you a double bond, and this right hand side will be getting a positive charge, so that you can get allyl cation as the product. Now similarly here also, if you see, if I break this bond on this side, I will be getting a negative charge here and a positive charge on this side. Again this positive charge, and here this negative charge will be getting you a double bond, and on the right hand side you can see a negative charge will be present. In radical system we all know that the bond will be breaking in homolytic fashion, so that 1 radical will be obtained at both of the ends, and you will be getting a double bond at one of the end, and on the other side you will be remaining with a radical species. Now we will see that how does in actual these 3 allyl systems are obtained back from the cyclic structure. So here at first we will be taking the example of cyclic to be converted into allyl cation structure. For that we should be knowing some basic things. The first of the thing which always should be known to us is that whether you are opening the closed structure or whether you are closing the open structure, in both of the cases the HOMO of the open chain structure is important, and that HOMO should be known to us, because that will be helping in opening as well as closing of the reaction. Now here we will see that in this cyclic cation structure how the ring opening will take place. So already I have said that we should be knowing the HOMO of the open chain structure. There are 2 pi electrons. So overall if you see in this system there will be 2 electron, and you have to see that what is HOMO in that. So if you see in allyl cation structure, psi 1, psi 2 and psi 3 star are the 3 molecular orbitals which we are having, and in the thermal condition The electrons are generally filled in such a way that our psi1 is HOMO. Now, whenever the reaction is undergoing the ring opening reaction in thermal condition, that case we have to always get the arrangement which has been shown here in this HOMO. That means these two terminal orbital which we will be showing after the ring opening, they should be having the same type of lobe on the same side. So this is our closed structure. So where the two same type of lobe has interacted, which forms the bonding orbital, or you can say which forms the bond out here. And when we are moving them, they should be moved in such a way so that the HOMO, that is psi1, should be obtained to us. So I am showing you the open chain structure out here. So open chain structure will be like this. So we should be getting the psi1, that is our HOMO. Now what should be the movement of these two orbitals? So if you see both of the positive lobes, they are on the outside. So if I move this orbital on my left hand side, certainly I have to move this orbital on my right hand side. That means this rotation is required so that this arrangement of psi1 orbital, that is HOMO, can be achieved for the product. The another very much important thing which we should be remembering is that the symmetry of the product and the reactant should be same. If you see, earlier we have said that in sigma bonding orbital there is always presence of M symmetry and C2 symmetry. So here if you talk about the product is having M symmetry, and as we just have said that in sigma symmetry orbital there is M symmetry as well as C2 symmetry. So we can say that the symmetry of the reactant is present in the product also. Now we will see that what will happen in HNU condition, or how does the HNU condition will be showing you the non-cyclized structure or ring opening reaction. So in HNU condition, again these three will be the orbital corresponding to psi1, psi2 and psi3, and the electron which is present at the lower energy will be excited to the higher energy level, that is psi2, and psi2 will become our HOMO. Now if you are going to open the orbital, in that case we should be knowing that after the opening of the orbitals, in that case the symmetry should be like our psi2 orbital, because that is our HOMO. So if I show it here, in this case you can see I have shown this particular open structure where I have shown the two lobes in opposite direction, and it is resembling the psi2 orbital of allyl cation. So I have to get this type of arrangement. Now I will see that how this arrangement can be obtained. So this arrangement can be obtained in such a way if I move this orbital towards my left hand side, and if I move this orbital towards my left hand side again. So if you move it like this, so it will go to my left hand side. That means the same type of rotation, or the rotation on the same direction is there. That's why you can say a cone rotation is required, so that I can get the side 2 orbital, and which is our HOMO. And if you talk about the symmetry is C2 symmetry in this case, and already we have said that in sigma bonding orbitals there is always C2 and M symmetry both. So you can say the symmetry is still preserved in the product also. Now we will see the case of allyl anion molecule formation from the ring opening of cyclic anion. So for that again we have to see the molecular orbital. So again here there will be three molecular orbital named as psi1, psi2 and psi3 star, that is your antibonding orbital. And first we will see that in thermal condition what will be the HOMO. And we already have said that HOMO is one of the important component for ring opening reactions also. As you talk about the system, so there are overall 4 electrons. So these will be filled in such a way so that psi2 will be our HOMO, and when you are opening the molecule in that condition, or the arrangement of the psi2 orbital should be achieved to us. So if I talk about the closed system, it will be like this, where the two same type of lobes has already interacted to give you a sigma bond. Now I will see that how can I get this side 2 arrangement. This side 2 arrangement, if I talk about, this is our HOMO for allyl anion in thermal condition. So here if you see the same type of lobe, they are on the opposite direction. So for that I have to move these two orbitals in such a way that they can give you the arrangement of this side 2 orbital. Now you will see that they both are moving in the same direction. So overall they are moving in the same direction. That's why you can say that cone is the rotation which is required by the molecule. And if you talk about a symmetry, here it is C2 symmetry, and in sigma bonding orbital, C2 symmetry and M symmetry both are present. Similarly, if I talk about the HNU condition, in HNU condition we all know that irradiation of the molecule take place and the electron from the outermost filled orbital get excited to the next level, so that psi 3 star will be our HOMO. Now, when we are opening this cyclized structure, in that case, we have to keep it in mind that in HNU condition, when the ring will be opened, this HOMO arrangement, that is of psi 3 star, should be obtained to us. So if you talk about the arrangement, here you can see the arrangement of the terminal orbital is of same kind. That means you can say that there is M symmetry. So we have to get this M symmetry after the rotation of the two orbitals, which has made this sigma bond. So if you talk about the movement of these two orbitals, you can see that in the product that same type of orbital are on the same side. So they will be just moving in opposite direction to each other, so that there will be this rotation, and psi 3 star molecular orbital arrangement will be obtained to us, which is HOMO in HNU condition for allyl anion system. Now the third type of example which we are having is the ring opening of cyclic radical into allyl radical. So likewise, in the case of allyl anion, we have seen the same concept is followed in the case of allyl radical also. So here again there will be three molecular orbitals, psi1 bonding orbital, psi2 non-bonding orbital, and psi3 anti-bonding orbital. Again we will be taking the thermal condition first. Three orbital in these, if you talk about the total electrons, so 2 pi plus 1 electron is here, overall 3 electrons are there, which will be filled like this. So we can say that likewise allyl anion, in case of allyl radical also psi2 is our HOMO. That means when we are opening the cyclide structure in thermal condition, the arrangement of these terminal orbital should be opposite to each other, or you can say C2 symmetry should be in the product. We can show it like this, where we can say that C2 symmetry should be achieved after the movement of the two orbital which has made the sigma bond. So if you see, there is C2 symmetry. Now I have to move these two orbitals, and how they can be moved? They can be moved in such a way. So one is moved on the left side, and if you talk about the another one, it is also being moved on the left side. So overall we can say that the rotation is of cone type, so that we will be getting the arrangement of side 2 molecular orbital, which is HOMO for the allyl radical system in thermal condition. Similarly, if we talk about the HNU condition for allyl radical system, here the electron will jump from its high energy level to the last orbital, and our psi 3 star will be the HOMO in this case. Again, when we are opening the closed system, in that case we have to remember that when the open system will be achieved to us, in that case the arrangement of the terminal orbitals should be like what is here in psi 3 star. That is, you can see if I imaginary cut the molecule from center, on the right hand side and on the left hand side same type of arrangement is there, that is M symmetry is there. So that means when we will open the system, here we should be getting the M symmetry. That means the same type of lobe should be on the same direction. So when this sigma bond will be broken, and when we are rotating it, in that case, if I rotate it in this way, that is one of the orbital going towards my left hand side, another orbital going toward my right hand side, in that case I will be achieving this M symmetry, which will be resembling the psi 3 star, which is HOMO for us in the case of H nu condition for these allyl radical systems. And here we can say that the movement is of this type. So here we have seen that how the ring closing and ring opening of allyl system can take place in thermal and H nu condition. And the most important thing is that whenever we are opening the structures or whenever we are closing the open chain, in that case, the HOMO of the non-cyclized structure is always important. The arrangement of the terminal orbitals will always decide that which type of rotation will be there and what type of symmetry will be present in the molecule. So we hope that this video certainly would have clear all the doubts of viewers regarding the HOMO and ring opening and ring closing concept, as well as it would have also cleared the concept of rotation and symmetry for you. So thank you for watching and don't forget to subscribe our channel. Thank you.